All right, guys. Good morning, and welcome back again to your long college algebra today. Happy Tuesday. I believe it is for you guys. As we get rolling into our lesson for today, as you noticed, I'm out. Feeling pretty under the weather, and I'd rather not get anybody else sick and take anybody down with me here while I'm out. So I have recorded a video lesson for 4.1. The good news is that I think it's a pretty straightforward lesson. We're going to sort of introduce some topics that we're going to spend a lot of time playing around with in the context of what we're going to see for Unit 4 with polynomial functions, but also start to describe like what on earth polynomials really are and what characteristics they have and how we can sort of use the methods from Unit 3 when we're working with quadratics, kind of graduate up a level to more general cases where maybe we got cubics or quartics or even quintics, finding roots, graphing, sketching, behavior, stuff like that. As we get rolling into our time for today, please make sure that you're bringing your phone up to the correct numbered slot in the phone caddy. The sub has instructions to make sure the students do so. So by all means, as you filter in for today, make sure that you get that knocked out. Normally, there is a feedback set of warm-ups here where we kind of check in as we wrap up the end of one unit and begin the process of launching into another. I think what we'll do is save that for when I'm back on for you guys Thursday. I'll also have for you guys graded and ready to get back to you copies of your summative so you can see how you did on the final closing remarks for what we're going to see for quadratics. What I do have are all of the quizzes and the quiz retakes graded. Those should be in PowerSchool, and if you notice that something's missing when you know for sure that you've taken one, definitely send me an email. Let me know, and I'd be more than happy to double check it. I've also graded all the classwork that's been submitted to me from either physical submissions or emailed pictures or the Schoology submissions. We should be totally current on our classwork. We're going to close out submissions here for Unit 4, rather Unit 3 as we move into Unit 4 and launch into polynomial methods. This is our last unit of material that's going to take us into our final exam in mid-December. We're not going to have a summative on this one. Instead, we're going to have kind of a big unit test that we're going to use as the final that will compare what we know with, say, units 3, 2, and 1 with some of the new things that we're developing as we graduate up and work with polynomial functions. For the final, that'll be kind of the last big ticket item in the gradebook, apart from a handful of quizzes and a handful of practice assignments. So we're more or less set as far as the major grades go for the semester. And as we go, we'll see some minor like tweaks and modifications. But you'll start to see things start to stabilize out to where we get a rather accurate prediction on what we're going to call our semester grades as we get ready to close it out and go to winter break. At a glance, this is what we're trying to do as we move into Thanksgiving break and coming out of it. I'd say that for Unit 4, we're going to have about 6 lessons of material. There's a lot of things to learn about polynomials, and there's a lot of connections back to what we're going to see with quadratics in terms of especially solving or finding roots or sketching graphs or working with the characteristics of these functions. But I want to start small. I want to kind of focus on like a really stripped down version of a polynomial that we call a power function. And I really want to focus on two kind of initial characteristics that these family of functions exhibit when we're talking about whether they are even, odd, or neither, and what their end behavior is like as we go out to the edges of the graph, which way do they go for the outputs. So that's our goal for today, is to arrive at a better understanding of what these terms mean, how to make determinations about how to sort and categorize different functions that are polynomials or power functions, but also kind of recap and review, especially end behavior. I know you guys saw that back in Algebra 2. The limit notation for that can sometimes be dense, and I want to make sure that we take our time with it and get kind of comfortable. Especially for those of you guys that are going to a STEM field, you're going to see a lot of that. So the earlier we can get very comfortable with that notation, the better, in my opinion. So moving into Unit 3, we have wrapped up a unit on quadratic functions. Quadratics most generally are a function in which we see this x to the second term. As we saw in Unit 3, sometimes in standard form, you've got like a linear terms like a plus 5x, or you've got a constant like a plus 6. We would refer to that as more of like a polynomial format, but it's still very much a quadratic equation. This highest power is kind of what dictates the categorization of the type of function that we're working with. We see that all quadratics, no matter what kind of things we can add on to them or subtract to them, what form they're in, what transformations are occurring, they all have this sort of general shape and behavior, right? They have this what we call parabolic behavior. This parabola is what we can sketch for a graph. Back in Unit 1, we also explored another function that's kind of similar in the sense that it's like x to the third, right? And x to the third is a little different in the sense that when you take a positive input and you go it times itself, it still comes out positive. And if you use a negative input, where you do a negative times itself, you end up getting a really large negative value instead of a positive value. So unlike, say, a quadratic whose domain is unlimited and its range is very much limited, with a cubic, you get a range that's very much unlimited. It goes up and down forever, right? Which is a different sort of pattern of behavior. And we're going to start to really explore some polynomials where we're going to see this sort of exhibited cubic behavior. We want to sort of develop some frameworks, some notation to kind of talk about these behaviors when the functions are maybe not quite so simple. Both of the functions that you've seen for f of x, either just x to the second or x to the third, are examples of what we refer to as power functions. A power function is essentially a constant times a variable like x raised to a fixed power. So n is like 2, 3, 4, 5. It's a number. It doesn't vary, it doesn't change, it stays the same power. It's the variable that's getting the power onto it that changes. What we want to do before we sort of graduate into larger polynomials is sort of focus on just the characteristics of this sort of simplified version of a polynomial. Here, what I want you guys to do is take a look at this Desmos activity that I prepared for you. You'll find a link for this in our course Schoology page. If you click on that link, it'll take you to this activity. I want you to sort of play around and modify some of the different sliders and some of the different values for the A term and the N term. And I want you to sort of make some observations with maybe an elbow partner. I want you guys to tell me, what do you notice is starting to happen with these functions? Are there certain like bins or categories you can put them into? What are the different settings for A and N that make certain behaviors happen? And we'll sort of pick up and we'll go from there. All right. So as we take a look at some characteristics of power functions, we've got here sort of an activity that I made in Desmos a long while back that I think is really good in the sense that it sort of illuminates the different patterns of behavior that we're going to start to notice at play here. We've got this sort of general function, y equals a times x to the n, where a and n are numbers that we get to set. We get to choose them, so sometimes they're referred to as parameters. If I choose n as 1 and a is 1, then my function is linear. It's this y equals x line that passes through the origin and has slope up 1 and over 1. Not terrifically exciting. We've seen graphs of linear functions since we were in middle school or in freshman year algebra 1. What I want you to think about are maybe its characteristics that are going to be shared with, say, different power functions. Now, if I take the slider for n and I adjust this from, say, 1 to 2, what you'll notice is I get a quadratic function out of this. I get this nice parabolic graph, and I have the function y equals 1x to the second. You get a very different kind of looking graph, right? It's very, very much different. Much more interesting behavior starts to emerge where the pattern of change is no longer consistent, right? You can't use a slope to graph a parabola. If I take this from, say, n equals 2 to n equals 3, you'll notice that you get the archetypical cubic function, where the further right you go, the further up it goes. The further left you go, the further down it goes. What starts to get a little interesting is when you go to higher powers, like, say, n equals 4, or n equals 5, or n equals 6, 7, or even maybe 8. Now, all those graphs look a little different, right? The higher the power goes, the faster the graph seems to be going up or down compared to how far it's going left or right. The graph of, say, x to the 8th here is very distinctly different than, say, the graph of x to the second. It's much quicker, right? It's a much steeper climb. But there is something that they both have in common. And what I want you to think about here with your group mates is like, what is it that you notice here about adjusting some of these sliders that keeps things similar, more so than say they are different? Now, one thing that might come to mind here is a conversation about something that we call end behavior. When you talk about the end behavior of a function, what you are essentially saying is how the function behaves as you go way to the left or way to the right. How it's, say, growing over time when time goes on, say as x goes off to the positive x direction or the negative x direction. One of the things that always trips people up with end behavior is that even though it's kind of a simple conversation, the notation behind it is almost incredibly dense. One thing that I have to think about is like which direction I'm going. We'll see here for like, say, x to the 8th, that the direction you're going in doesn't really matter. If you go further to the right on the graph, what I want to point to your attention is that you're going the larger positive x direction. You're going towards positive infinity, way out there in that direction. Similarly, as you go way to the left, you're going in the larger negative direction, which is to say that you're going towards negative infinity, off in that direction. That is a very important detail that we want to keep track of when we're having conversations about end behavior. There are some functions which will have very different answers about their end behavior that depend entirely on which way you're going. Are you going way to the left or are you going way to the right? The way that we express to the reader that we're going way off in one direction is to say, okay, which type of value is x going towards? And we express it with a keyword that we call the limit. This is going to show up for a lot of you guys in pre-calculus or calculus courses in like a STEM field all the time. So it's good to get comfortable with what this is trying to say. The limit as x goes to infinity is saying even though you can't get to infinity, keep going after it. Keep chasing it, keep following it, right? Keep taking that extra step in that direction, and then report to us what's happening to your function. So if I label my function here, say f of x, and I want to know what f of x is doing as I go way to the right, the way that we express that is the limit of f of x as x goes to positive infinity. And we say what it's trending towards. Now, if I trace this graph from left to right, what I'm going to notice is that the further right I go, the further up this graph is going really, really quickly, right? So I would say that if that's going up in the positive y direction, it's going towards positive infinity. And similarly, if I had a graph that was going down really quickly, I would say that it's going off in the negative y direction towards the larger negative numbers, and I would say it's going towards negative infinity. But you'll notice here for this graph that the behavior matches. If I go further left on the graph and I just sort of trace it out with my finger, I'm going to notice here that the limit as x goes backwards towards negative infinity in the x's is still infinity. It's still going up, right? Now, that might be more familiar than the conversation that we're going to have with like end behavior. So I wanted to kind of hit this topic first. You'll notice that it's like the second thing we talk about in the notes. I don't think that's a good idea that they ordered it that way. I would almost flip that if I were printing these myself again. So end behavior, we use this sort of dense notation to say what's going on as you go off to the edges. What I want you to notice here is that if I take a look at, say, end of the 8th or the 6th or the 4th or even the 2nd, there's really no difference in the end behavior, right? They all do the same thing in the same direction. If you look at, say, like n equals 1, which doesn't really feel like a power function, right? It looks more like a linear function. But you also compare it to n equals 3 or 5 or 7, you'll notice something a little bit different. Now, if I'm expressing the end behavior for these functions, I've got to be careful and tell the reader which way I'm going. So either x is going towards negative infinity, I'm going way to the left, or x is going towards positive infinity, I'm going way to the right. But I've got to tell the reader that. I've got to be really specific here, right? If I call this function f of x, and I can say the limit of the function f of x as x goes to negative infinity or to positive infinity is what the y values are trending towards. If I go off to the right, you'll notice that my graph is trending up towards positive infinity in the y's. But it's different if I go to the left. If I track the changes as I go to the left, I'm not going up anymore, I'm going down towards negative infinity. And you often see me like describe this as sort of split end behaviors. I go one way, I get one answer. As I go another way, I get something different. There's something to do with the power of the function here that makes that occur the way that it does. You probably noticed that when all the powers of these power functions are odd numbers, you're going to get split end behavior. As you go to the left, you're going to go down. As you go to the right, you're going to go up. Whereas all the even functions both go up forever. And if you think about what's going on there, like if I do say like x to the sixth, and I wanted to know the end behaviors that go off to the right, well, choose like a number like 3, right? If I do like 3 to the sixth, that's the same thing as like 3 squared times 3 squared times 3 squared, right? If I square something, it always comes out positive. So 3 by 3 is 9. So this is like 9 by 9 by 9, which is like 81 by 9. You get a big number, right? Which is why it goes up so fast. If you think about a negative number, though, you can think of 3 to the sixth as like negative 3 squared times negative 3 squared times negative 3 squared. If you do a negative times a negative, think about what that's supposed to look like. It's supposed to switch to being positive again, right? So when the power is even, even the negative inputs eventually go back to being positive outputs. So it doesn't really matter which way you go because of that even number of powerings that happen on the negative term. So that's why that occurs the way that it does. You'll notice something different though. If I take like a power function, say x to the fifth, and I adjust the slider for a. If I adjust this to say like 2 or 3, I'll notice that it goes a little faster in the y direction, but notice if I take it from say a positive to a negative number, something has flipped, right? If I say a is like -1, then the solid graph you can think of as having undergone a reflection over the x-axis, like we see with other functions, versus say the dashed line, which is what happens if, say, I don't have that negative a on the front of this, so I don't have the reflection present. What you'll notice with that solid line is that the end behavior switches. If your graph is upside down, then as you go to the left, you go up forever to positive infinity. And as you go to the right, you go down forever to negative infinity. That's going to be the case. Whenever that a term is a negative, it's going to kind of flip things around with your end behavior. You'll see something really similar with even power functions too. To kind of illustrate that, right? Let's take a look at like x to the fourth when the a is negative. You'll notice instead of opening up really quickly, this thing opens down really quickly. And the reason for that is if I choose like say x equals 3 and I do like y equals negative 3 to the fourth, well, I have to do 3 to the fourth first, right? That's going to be like 9 by 9, which is 81. And then I have to make the result negative, and that's why it goes down instead of up. The negative on the outside is the last thing to happen on the input. So it flips the sign from whatever it started as and makes it the opposite. So end behavior is probably the more like familiar of the two behaviors that we've seen so far. I wanted to spend a little time and hit this first before we dive into maybe the next part. So as we sort of collapse together, like all the things we've learned so far about power functions and some of their behaviors, you'll notice in our notes that there's kind of like an organization, there's like a table where we talk about two things with power functions. We talk about the exponent, which we call the power or the degree of the power function. We talk about this a term that we call the leading coefficient. If I introduce the limit notation here, what I tend to do is like write in plain English underneath it what it's meant to say, especially in the beginning, just to kind of serve as training wheels to get people comfortable with what we're looking at there. You'll notice that when n is even, or you have an even powered function, whether you go left or right doesn't make a difference. Your end behavior matches. When a is positive, it goes up. When a is negative, it goes down. Odd powered functions, though, that's a different story. If you have an odd degree to your function, you'll notice that you have split end behavior. So you should never have it matching, right? Whether it's down and up or up and down, they should always be in disagreement, right? One's going to go one way and the other one's going to go the other. If A is negative, the further right you go, the further down the graph goes. The further left you go, the further up it goes. If A is positive, the further right you go, the further up it is. The further left you go, the further down it goes. Now, that's one part of what we're going to see in the notes. There's something else that gets introduced and explored that I think is maybe the more tricky part of what we're going to see for our notes today. So I wanted to take a moment, kind of slow down a little bit, and maybe emphasize like the more familiar territory before I got into maybe some of the newer stuff that we're going to see with this discussion about like evenness, oddness, or neitherness. If you take a look at the graph of some of these functions, one thing that you'll notice for say like, I don't know, x to the second is that it's a really nice symmetric graph, right? If you think about the way that it's symmetric about the y-axis, right? This bit that I'm kind of like swirling over in this like cyan color. The axis of symmetry is the line x equals 0. And we saw a lot of that when we were working with quadratics in Unit 3, right? Now, there's an interesting property that's going to emerge for functions when we see this sort of symmetry. If you choose a coordinate on one side, say the coordinate 1, comma 1, it has a mirror image, right, on the other side of the axis of symmetry. In this case, the coordinate -1, comma 1. If I choose another one, I'll see a coordinate here that's like 2, comma 4, has a mirror image on the other side of -2, comma 4. What I want to point out here is like the thing that's the same and the thing that's different about the coordinate notation. If I have an over the y-axis reflection, right? And I'm thinking about how to change coordinate by coordinate every single thing about the function. Well, if I wanted to get the mirror image and I have the initial coordinate, the way that I can change it is to keep the y value the same, but change the input to be the negative version of what I started with, right? Or thought of a different way, you can think of just like switching the sign on it. That's always true for these functions that exhibit this sort of symmetry over the y-axis. So if I'm thinking about like notation where instead of like x and y, I've got like x and f of x, what you're going to notice here is that every coordinate x comma f of x is corresponding to a coordinate like negative x comma f of x. Now, one way that we can sort of develop a way to check whether a function is going to have the symmetry is to say, okay, let's deliberately test a negative version of the original input for the function and see what happens, right? So if my original function, f of x in this case, is like 1x to the fourth, and I test it with, say, negative x, what I'm going to notice here is that my answer to my problem is now negative x to the fourth power. But what's going to happen to the negative? Well, negative x times negative x times negative x times negative x is positive x to the fourth, which is exactly the same thing that I started with, right? So there's sort of a rule to check whether a function is going to have this sort of symmetry. If, when you plug in, say, a negative version of the coordinate to your function, you get the exact same thing back out, then what that means is that this is what we refer to as an even function. That's the same thing as saying that it has an over the y-axis reflexive symmetry. So even is kind of a shorthand here for the type of symmetry the function exhibits. We don't necessarily tie that to like the power of the terms that we see in the function, because we'll see later with polynomials it gets a bit more complicated. But anytime you see that this type of symmetry is there, you can say that that function is a type of even function. Now, what I want to point out here, maybe on the other side of the coin, is a function like x to the third, in which that's not really true, right? If I were to try and draw the mirror image of this over the y-axis, I get something that's not mapping back onto itself, right? So if my red line is the original and the dashed line is the mirror image turning like the page of a book over the y-axis, they're two totally different functions, right? They're not even close to being the same thing. Now, if you think about this a little bit differently, and you think maybe about a different sort of symmetry, there is something kind of interesting happening. If you look at a coordinate like 1, comma 1, and say this guy here at negative 1, comma negative 1. If you think about like taking your notebook and grabbing the top with one hand and the bottom with another and turning it like a steering wheel so that your hands swap, so you turn it 180 degrees, you'll notice that this graph maps perfectly back onto itself. So it's not so much like a mirror image type of symmetry, so much as it's a spinning or rotational symmetry, like a propeller. So if I turn the graph 180 degrees and it maps back onto itself, that's another important type of symmetry that we're often interested in studying in mathematics. We refer to that as an odd symmetry. Now, I want to sort of highlight like what's going on with the coordinates, right? I started off with the coordinate x comma y, and it became a coordinate negative x, negative y. I changed the sign on both instead of just one of them, right? If I'm maybe working back into like x and f of x notation, what you're going to notice is that the analog to that is that x comma f of x, the original coordinate, is going to become negative x comma f of negative x. But when I do f of negative x, that turns out to be like the negative version of the original y value. So a different way to express that is to say it's just negative of f of x. We refer to this as a rotational, where in particular we're turning like 100 degrees, a rotational type of symmetry when this pattern emerges for a given function. When we think about like coordinate by coordinate, turning things over 180 degrees, hand over hand, like turning a wheel, right? We'll notice that this occurs with some functions and that it's just a different sort of symmetry. So these are kind of serving as some ways of looking at whether there's a symmetry or not to a given function. Sometimes you'll see them, and sometimes they're just not even there. This idea about how the coordinates are getting modified is going to serve as kind of the backbone for how we sort of verify and check whether a function is even, odd, or maybe even neither. Now, the idea that we can do this like coordinate by coordinate and get these sort of conditions that we're checking actually goes back to your geometry class a long time ago. Back in geometry, one thing that you guys were talking about was like, say, for certain shapes on the XY plane, on the Cartesian coordinate system, how do you change or modify a shape to get a new one, right? Where you have triangle ABC, and you're trying to convert it somehow into triangle A prime, B prime, and C prime, right? Sometimes you flip it, sometimes you rotate it, sometimes you translate it or move it around. Those transformations, those geometric transformations are very much still at play here. We're just kind of thinking about the functions in more coordinate notation. So knowing that these facts should be true for even or odd functions is a really important part of understanding how we sort of work with polynomials and power functions. It's something that we want to get comfortable with. But we'll practice it both ways. We'll kind of practice it with graphs, and we'll practice it with the more algebraic notation. Now, all of this with power functions, right? With just a single variable to a fixed power is going to sometimes apply to the larger family of functions that we call the polynomials. A polynomial, the best that I can think of, is a general class of functions where you have a bunch of power functions adding and subtracting together. They all have different leading coefficients, they all have different exponents, but it's just a big sum of them, and you get some really complicated behaviors that emerge from them as you take a look at their characteristics. A lot of the factor form polynomials that we'll see are going to come up when we're in the context of like solving or finding roots or zeros. We'll get to that when we get there. What you'll notice for the rest of the notes is that you're going to be given some functions in standard form, and we're trying to make determinations about whether they're going to exhibit a certain kind of symmetry, but also talk about the end behavior of the graph. Again, I want to approach this a couple of different ways, both an algebraic way with the conditions that we can check, and a graphical way to kind of verify it and prove it to ourselves that this works and kind of serve as a bridge between the two. So let's say I've got these three functions. I've got f of x, g of x, and h of x. They're all polynomials of some kind. The first two are two-term polynomials where I've got a higher powered term plus a lower powered term. H of x is the cube root of x, so we might better call that just a cube root function. But if you think of the cube root as like the 1/3 power, you can kind of technically sneak it into that family of polynomials, but it's more there to sort of serve a visual purpose that we'll explore here in just a minute. Now, I want to work with the function f of x, and I want to determine its end behavior, and I want to determine whether it's even, odd, or maybe neither one. One way to do it is to graph the function and take a look at it and see if it exhibits either a rotational or a reflective symmetry. What I notice here is that if I were to sketch, say, a line going down the y-axis, this function in red is a perfect mirror image of itself over that line. If I take one of them and I flip it over, I get the other one out for free. So we've got this sort of symmetry over the y-axis where like one part of the graph is the mirror image of the other. That's going to tell me right off the bat that f of x happens to be an even function. Now, I'm also interested in thinking about how to check it in maybe a more algebraic sense. An even function is even if, when I give it a negative version of the same input, I get the exact same y value out of it. So that's to say that f of negative x, where I deliberately change the sign on the input, is really no different than the original output f of x. They're one and the same thing. So to sort of check that out, what I'm going to do is grab the rule for my function, which is something to the sixth, plus 4 times something to the second, and I'm going to plug in negative x for both of these gaps. I want to see what I get, whether it's the same function or something different. Now, what you'll notice is that a negative number times itself an even number of times is going to switch to a positive number, even if you don't know what that number is yet. Negative x to the sixth is going to look like plus x to the sixth. And 4 times negative x squared is going to look like 4 times positive x squared, which is the exact same thing as what I started with. So I know for sure that this is an even function because switching the sign on the input has no effect on the output. They're exactly the same thing. Ultimately, that corresponds to this mirror image sort of symmetry. Now, as I go to a different function like g of x, things get a little more interesting here, right? I've got this cubic term plus this quadratic term, and I get this big wiggly looking sort of S-shaped curve here that's very different than anything we've seen before, right? If I'm thinking about whether it has like a reflective symmetry over the y-axis, what I would want to maybe graph is the original and a version where, say, I switch the x values, but not the y values. And I compare the graphs to see if they're identical or if they're different. What you'll notice here is that they are most certainly not the same thing, right? Those are two very different graphs. So I know for sure that g of x is not an even function. If I were thinking about like a 180-degree rotation, and I were to imagine like grabbing the graph at like 12 o'clock and 6 o'clock and turning my hands over each other 180 degrees, what I'm going to get is, albeit imperfectly, because I'm kind of imagining what this is looking like, a graph that looks maybe something kind of like, trying to see how this would work. A little harder than I thought, maybe. You'll have something that goes like up and to the right, and then you'll have like this branch on the right-hand side kind of going down forever to the left, and you'll have to like bounce off of, there we go, this point at the origin, right? So you get something that looks kind of like that, which is not the same thing, right? It's a very different graph. And for those of you guys with like a graphing calculator, if you want to do this on your Chromebook with Desmos and like literally turn it end over end, you'll notice that you get a graph that looks completely different. It doesn't map back onto itself. So this is an example of a function that we would say is neither. It's not even, nor is it odd. It doesn't have reflective, nor does it have rotational symmetry. If I wanted to prove that, well, what I could think about is what happens when I give a negative input to g of x. If I give a negative input to g of x, and I've got a negative number cubed plus a negative number squared. The negative number squared is going to switch to being positive, so that's plus 4x to the second, but the negative number cubed is still negative. And this isn't the same thing as what I started with, right? So it's not even. It's also not the negative version of the original function. So if I'm thinking about like the condition that I'm checking against for oddness, what I want to see is that f of negative x is the same thing as just the negative outputs of f of x. And if I wanted to say what the negative f of x was going to look like, well, I take x to the third plus 4x squared and I switch the signs on all of them. And I'll notice it's close, but it's not really the same thing, right? I get that negative first term, but I don't get the negative second term. So it's not odd and it's not even. It exhibits neither type of symmetry. And that's going to happen pretty commonly, actually, with most polynomials that you work with in the wild. Now, let's say that I want to graph the function, the cube root of x. Again, a lot of these are for Desmos. This is not something I expect you guys to graph by hand. I want to take a quick look at the sketch of the graph and say, okay, what kind of symmetries do I see are present? If I try and flip it over the y-axis, like turning the page of a book, you'll notice that the original is the dashed line, the solid is the flipped version, the reflected version, and they're not the same thing. They're two very different graphs. So no even symmetry, no reflective symmetry. If I think about, say, like a rotational type of symmetry, though, where I choose some of my coordinates at, say, 1, comma 1 and negative 1, comma negative 1, or say 8, comma 2 and negative 8, comma negative 2. If I take my graph and I rotate it 180 degrees about the origin, I see that I get a perfect mapping of the function back onto itself. It looks no different than what I started with. They look identical. That's an example of something that has that rotational symmetry. So we would refer to that as an odd function. Now, if I wanted to think about how to prove that and sort of verify what's going on with that, there is an algebraic way to do it. What I'm going to do is feed this a negative input and see what happens. A lot of people get tripped up with the cube root function I think a lot of people maybe think about the square root function and how that behaves and think that this is similar. They're actually quite different. The cube root of a number asks us to answer the question, what times itself is this thing underneath the radical, right? So the cube root of 8, I would understand to have the answer of 2 because 2 by 2 by 2, 2 to the third, goes back to being 8. Can you take the cube root of a negative number? If you think about a number times itself, that's negative 8. Can you think of one? And what you'll notice here is that the answer is negative 2 because negative 2 by negative 2 by negative 2 is negative 8. So you can take the cube root of a negative. Some people will look at this and go, how on earth am I supposed to do that? It's undefined or it's imaginary, right? But that's actually a property of square roots, not cube roots. Very, very different functions, right? Now, if I want to think about what happens here with like the type of inputs and the type of outputs that I'm getting, notice that when I started with a positive number, I got a positive number out of it. When I started with a negative number under the radical, I got a negative number out of it. So if I wanted to take the cube root of negative x, that would be the same thing as the negative answer of the cube root of positive x, which is not the same thing as what I started with, right? And that's why it's not even. But if I think about the negative version of h of x, then an input of negative x gives me a corresponding negative output compared to the original. And that's why it's an odd function. So there's kind of some strange naming conventions with these, right? Even and odd functions. We usually think of even odd with numbers or even like parity in certain other scenarios. It's kind of a weird way of describing functions. So sometimes what I find is helpful is to go back to maybe more familiar terminology. Even you can think of as reflective symmetry, like turning your hand or the page of a book. Odd means that there's a rotational symmetry. That is, you turn things like a doorknob 180 degrees, you map right back onto yourself with your function. They're really one and the same. So to kind of put it all together, right, we've had this discussion about end behavior with power functions in particular, not really polynomials yet, right? And we've had this conversation about evenness and oddness of functions with power functions and with full-on polynomials. We haven't really put them together yet, all at once. So what I want you to try real quick as we close out the notes is this example, or these sets of examples where you've got, say, with the typo present and everything, three functions, f of x, g of x, and h of x. You notice here that they're all general polynomials. So there's a sum of a bunch of power functions all operating together. Try graphing them and see what you notice about the end behavior and their oddness or evenness. Try sketching a graph and taking a look at it that way. And we'll sort of bring it back in and discuss like a more algebraic approach. And that'll close out our notes for today. All right, so we've got these three functions. They're all polynomials. There's some crazy terms with different powers flying around. Some are positive, some are negative, some are even powered, some are odd powered, or their degrees are different. Uh, we're trying to bring it all together, right? Conversations about both end behavior and conversations about evenness, oddness, or neitherness, right? The types of symmetry that we see exhibited in these graphs. I have temporarily disabled graphs for g of x and h of x and Desmos just by kind of clicking on these buttons to the side of them. Nice thing about Desmos is it can handle a lot of graphs at once. I'm eventually going to re-enable these and we'll take them one at a time, but I want to start with maybe this function f of x. It's pretty complicated. There's a cubic term, there's a quadratic term, and there's a constant, right? It yields this weird, wiggly, sort of S-shaped graph that vaguely kind of looks cubic at the edges, but there's some more complicated behavior there in the middle, right? Now, what we're trying to determine, maybe first off, is end behavior, right? Notice that as you go way to the right on the graph of this function, you are traveling towards positive infinity, and the y values are going up forever to positive infinity. So if I wanted to express the end behavior of this as x goes to infinity, I'd specify that the function f of x is what I'm working with. I'm going way to the right, and I'd say that I'm going up forever to positive infinity. The limit of f of x as x approaches infinity is infinity. I'll do something similar in the negative x direction as I go way to the left with this particular function. I'm going to notice that I go down forever towards negative infinity. And I got my end behavior. That's the end behavior for like an odd degreed function. And you'll notice that I'm specifying, right? Like even and oddness versus even odd degree. There's not necessarily only an odd degreed term in the function, right? There's a quadratic term in addition to the cubic term, but its end behavior is matching something more like a cubic. We'll kind of talk about why that is on like our last example there with x to the 11th. Suffice it to say, though, from the graph, I can get the end behavior pretty quickly. If I'm thinking about like evenness or oddness, that's where things get a little more interesting. I could notice for this particular function, and actually now I'm curious, I want to know if I take like f of x and I do in Desmos like f of negative x. Oh, look at that. That's cool. I didn't know it could do that. Oh, you learn something new every day. What you'll notice here is that you can get the mirror image of the function pretty easily. If you say f of x is this rule, and then you just give another one that says f of negative x, boom, there are the graphs, and you'll notice they're not the same. So f of x is not an even function. It doesn't exhibit that reflective symmetry. Similarly, you will notice that f of negative x is this dashed line. I'm going to temporarily disable f of x, and I'm going to graph negative f of x. I'm going to graph like its negative image, which is like its rotation around the origin 180 degrees. These things are not the same thing, right? If I take the original function and I compare it to, say, its original, right, where I take the topmost one, I rotate and spin it around counterclockwise, they are not the same thing. So it is neither even nor is it odd. And we can kind of show it graphically, but we'll sort of work into some more algebraic demonstrations as we go to some later examples. So we got our answer there, right? F of x, it's neither. If I think about g of x, I get a different polynomial function where I get these sort of like camel humps on the side, and there's this little divot in the middle. It's a nice symmetric graph, though. It's definitely got that mirror image over the y-axis symmetry, so I know it's even right off the bat, right? If I'm thinking about end behavior, what I'm going to notice here is that it goes down forever, regardless of whether I go to the left or to the right on the function. So if I wanted to express its end behavior, I need to say very carefully, which way am I going? That's always important with these. I got to say the limit of, which is the key word for end behavior. And I got to specify to the reader on the other side of the equal sign which way we're going. In this case, we're going down. So that would clue me in that maybe like the leading coefficient is like a negative number. And we see that that's definitely true. It's a -4 attached to x to the sixth. Something you'll notice here is that all the terms are even, at least even powered degrees, I should say. X to the sixth, x to the fourth, x to the second. So again, we're kind of getting an answer graphically without necessarily like thinking about deeply what's going on in the structure yet, right? We'll sort of switch gears here as we hit this last example for h of x. This one's kind of interesting. H of x is three terms. So you can think of it as like a trinomial or just a general polynomial. It's got an x to the 11th term, which is an odd degree. It's got an x to the 7th, which is an odd degree. And it's got x to the first, which is an odd degree. Its end behavior is kind of like that of a cubic, but it's upside down, right? As I go to the right, it's going down really quickly. As I go to the left, it's going up really quickly. So if I wanted to write that out, I could say the limit as x goes to infinity of h of x, got to specify which function we're working with, goes to negative infinity. Meanwhile, as x goes to negative infinity, so as I go way to the left, my function goes up to positive infinity. I'm just using the graph to do it though, right? I'm not really like digging deeper into the structure of the function and why it does that. Now, that's where I want to pause and kind of go on a digression about why that works. You'll notice for f of x, right, that there was an even powered term and an odd powered term. The other ones are either all even degrees or all odd degrees. So the question kind of remains like, well, why was f of x, say, more cubic in structure versus, say, more quadratic? In order to help answer that question, what I want to do is sort of think about it like numerically, right? What it means when we say x goes way to the right or way to the left in a more numerical, calculator heavy way. Let's let x be a big positive number, like 1,000. If I wanted to figure out the output for x equals 1,000, I have to plug it into that rule and see what I get. I can make a guess that I'm going to get a huge positive number out based on the shape of the graph, right? But let's actually run it out, at least a little bit, and see what happens. F of 1,000 is going to look like 2 times 1,000 times 1,000 times 1,000. That's going to be huge. And then I've got this minus 3, 1,000 squared term, right? 1,000 times 1,000 is big, but it's not enormous, right? It kind of gets swallowed up by this enormous positive number to its left, and it looks like a huge positive result. And then I add 5 to it. The plus 5 is hardly going to put a dent in that, right? So that is ultimately a very large positive input, yielding to a very large positive output. Let's do the same thing maybe with a different choice of x, but let's let x be a really big negative number, like negative 1,000. Well, if I evaluated f of negative 1,000, I get 2 times negative 1,000 times negative 1,000 times negative 1,000. That's a huge negative number, right? If I think about what comes next, where I do minus 3 times negative 1,000 squared, negative 1,000 squared switches to being positive and big, times negative 3 is a negative big number. So they're maybe not like competing with each other as much. Then I've got this extra plus 5 flying around, right? What I want you to think about is like which one of those is really calling the shots. A big number is big, sure, but a huge number is like orders of magnitude larger. It's like hundreds or thousands of times larger. So even if you add or subtract something onto it, it's not really going to make it feel all that different, right? That's ultimately what happens with end behavior. When you think about the function, it's the highest powered terms that call the shots for the end behavior. So even if you have both even and odd degreed terms, the largest power calls the shots when you go way to the edges towards the really large positive or negative inputs. So if I wanted to look at f of x and notice that it's a cubic polynomial, the cubic being the leading degree, I know it was going to have the split end behavior. If I look at g of x, where I see the largest degree is 6, which is an even number, I know it's going to have matching end behavior, either up, up, or down, down. And if I look at h of x, I see x to the 11th by a long shot beats every other power there. That's an odd number, so it's going to have split end behavior. That's how you can make that determination quickly. It has everything to do with the highest powered term in the front. Let's maybe have a conversation kind of briefly about like evenness or oddness for like this last function, right? If I take a look at h of x, what I'm going to notice is that it's not a mirror image over the y-axis, so it's not an even function, but it does seem to exhibit odd behavior in the sense that if I take a coordinate at like 1 comma negative 2 and I rotate it counterclockwise 180 degrees, I get 1 comma negative 2. Sorry, I think the original is negative 1, 2, there we go, and this new one is 1 comma negative 2, there we go. Now, to verify it algebraically, right, we want to deliberately give h of x a negative input and see what we get. I'm going to have negative 2 times negative x to the 11th minus 5 times negative x to the 7th minus 4 times negative x. Negative number to the 11th is going to be like a negative something to the 11th. But the negative part multiplies with the negative 2, and that switches to looking like positive 2x to the 11th there. If I think about negative x to the 7th, negative something to the 7th power is going to look like a negative number, but if I multiply that by negative 5, it's going to look like positive 5x to the 7th. And then the last term, right, negative 4 times negative 1 times x is going to look like plus 4x. You'll notice that it looks identical to h of x. It's just that we switched the sign on all the terms, so instead of negatives, every single one of them was positive. That's the same thing as negative h of x. So if h of negative x yields negative h of x, if changing the input sign results in the outputs flipping, that's evidence that it's an odd function, that it's exhibiting that rotational symmetry. Just kind of a different way to check it out, right? It's a new skill, a new one, and it's kind of a weird conversation that we've been having around that, right? Would not necessarily say it's like an intuitive thing to pick up. So as we get rolling into our time for today, I'm hoping that when I come back on Thursday, I should have lots of information about how Unit 3 wrapped up for you guys. We'll do some feedback. We'll kind of touch base and see how it's going with 4.1. Maybe work a couple more examples just to make sure everyone's on track. In the meantime, though, I hope you guys enjoy the rest of your day. I hope to see you guys soon. I definitely would rather be in the class and kind of giving you guys the feedback. But otherwise, I'll see you guys on Thursday. Take it easy.